Students' learning experiences have changed considerably over the last decade. Really, they're always changing, but there's been a lot of changes in particular. And along with that, the data we have on students has also changed. One big development, interactive learning environments of various sorts have existed for a while, but they've really started to increase in how often they're used. Like systems like LearnSmart from McGraw-Hill, or ALEX, which is a system used in college math and college chemistry. Simulations like INKITS. This was developed right here at Rutgers by Janice Gobert in the Grad School of Ed. Games like Physics Playground, where students learn about physics concepts by, in this case, drawing drawings that come to life and operate to solve puzzles that require understanding of physics. 3D virtual environments. There's such a variety of environments that students learn in these days. Also, massive online open courses and non-massive online open courses, although at this point I feel like the difference between so-called MOOCs and other online courses is really the open and free versus other aspects, but these have become really a big part of modern education at a lot of universities. They generate voluminous quantities of student log data. Pretty much everything students do in these environments is tracked, which allows us to see what's going on much more easily than we could when we were handing out assignments on paper. People have also done research with grade and outcome data. Again, one of the transformative factors on that, we've had grades for a long time, but when they're all in a computer system and you can track a student's trajectory across time, it becomes something very different than when they're kind of all separated from each other. Student engagement data. Monica was kind enough to mention our BROMP handheld app and protocol for field observation. That was used, for example, they did over 60,000, I think, 60,000 is about the number. I've forgotten the exact number. 60,000 observations of students in the Corporation of Chennai in India. So here we have a setting where there's no instrumentation, there's no computerization. It's a more traditional pedagogy, but they're able to collect large-scale data on engagement and use that to determine which pedagogies are working more effectively at engaging students. That was actually used in some reform efforts there to switch from traditional recitation curricula to more hands-on science activities and demonstrate that that led to higher engagement. National Student Clearinghouse. Who here's heard of the National Student Clearinghouse? Yeah, about half the room. Big database where it was originally created for making sure students weren't getting financial aid from two places at once. That's now been used to track where students go to college for longitudinal research, to figure out which interventions in middle school lead to better results in college. PAR framework, who's heard of that? That's a little bigger on the West Coast, but it's an initiative across many large universities to share and collaborate on data on student course taking and success. These are just a few examples, but they all represent large-scale data. You get things like log data from systems used by hundreds of thousands of students a year, systems like ALEX, the Cognitive Tutor Assessments. You get whole university system data on course taking and student outcomes. Along with this expansion in data, there's kind of grown up two different scientific societies, the Educational Data Mining Society and the Society for Learning Analytics Research, who are looking at the measurement, collection, and analysis and reporting of data about learners and their contexts to understand optimized learning and the environments where it occurs. So these societies have a joint goal of exploring the big data now available on learners and learning, and I put big data in quotations because people disagree about what big data is, and the definition changes over time, right? In education, we have these 4 orders of magnitude bigger data sets than we had available to most people even a decade ago. But at the same time, when you compare our data sets to Google, they think that our data sets are these tiny little things. People in these fields use this data to promote new scientific discoveries, advance the science of learning, better assess learners along multiple dimensions. I'll talk about this more in a minute. And better support learners trying to get towards genuinely individualized instruction. There's broadly 5 types of EDM learning analytics method. I'll talk about each of these in a sec. Prediction, structure discovery, relationship mining, what these papers call distillation of data for human judgment, but despite the fact that's my term, visualization is probably a better term. Not a great idea. And discovery with models. In prediction, we develop a model that can infer some single aspect of the data, the predicted variable, from some combination of other aspects of the data, like the predictor variables. So for example, trying to infer which students are bored during learning, or trying to, just from their interactions, or trying to figure out which students are going to fail the class, so we should try to help them. You try to, in this case, infer something that matters so you can do something about it. A second category is structure discovery. People tend to get really excited about this one. In many ways, it's actually a weaker method than the first set. But find structure and patterns in the data that kind of emerge naturally. You just throw the data at the wall and some stuff kind of sticks to the wall and other stuff kind of doesn't. There's no specific target or predictor variable. So for example, in say a college math curriculum, which problems actually map to the same skills? We may have created a lot of problems which we think actually are the same skill, but maybe students get one of them right and the other one wrong, and they're not actually that correlated. Are there groups of students who approach the same curriculum differently? There may be different strategies that students use, or there may be different prior experiences that cause some students to have a very different path. Which students develop more social relationships in massive online open courses? So we can look at the structure of communication between people to figure out where they're grouping differently. Relationship mining, discovering relationships between variables in a data set with many variables. Those of you who, probably most of you who took an introductory statistics class may have had an instructor who said data mining is bad. And what they meant by data mining was just trying a whole lot of patterns and seeing what came out. And that is bad if you've got a small data set. If you have 400,000 students, you can probably do this much more safely. There are methods for making sure that your conclusions are still valid. So for example, are there trajectories through a curriculum that are more or less effective? One example of that might be that you might have, say, choices in your computer science undergraduate sequence where they can take A then B or B then A. Which one leads to better results? Which aspects of the design of online learning have implications for student engagement? I'll give a couple examples of that later. But we can actually take all the features of different content and figure out what content is associated with better engagement. As perhaps that very, very brief review of methods might indicate, there's a lot of applications for this. Prediction of student dropout or success, automated detection of learning, engagement, emotion, strategy, and so on for better individualization, better reporting for instructors, academic advisors, other stakeholders, basic discovery, scientific discovery in education and learning. Let's start with the first one. Many modern systems can predict dropout or course failure. I just heard that this is not a campus that tends to have a university-wide initiative in this, but a lot of universities, for example, go to vendors like Civitas or Zogotech or Course Signals or Sumo to get this kind of technology, and then they deploy it. Yes, sir?
We have EAB. That's what we're using.
Okay, got it. Thank you. Got it. Yeah, EAB I didn't put up on the slide, but they're probably actually, I think they're bigger than any of these except for Civitas. Actually, I don't know why I didn't put them on the slide. But yeah. Okay, so Rutgers does have that.
Yes.
Good to know. So some open issues. First of all, which predictors are actionable? Like a lot of these systems succeed by exploiting predictors that actually aren't very useful. So the best prediction in terms of numbers can sometimes involve predictors that aren't useful, and in that case, what do you do with it? What are some examples of this? Well, demographic prediction. If you predict on the basis of demographics, it becomes much harder to figure out what to do for an individual student compared to predicting on the basis of, say, who hasn't been posting to the discussion forum, or who hasn't been showing up to class, or who actually bombed their first assignment or started the day before it was due. Is a model fair and equitable? Some vendors, not all, some vendors don't check their models for whether they work equally well for all subgroups. I actually don't know whether your vendor does that. I don't have good context at EAB. If you don't check, then you have this risk of having a model, and my colleague Josh Gardner has written very compellingly about this. You can have a model that works really well for, say, one group of students, but not well for a specific group of historically underrepresented students. That's particularly a problem when your model is, say, got only 3% of the data that went into it is historically underrepresented students in that group. The model does a great job on the 97%, does a bad job on the 3%. Some models explicitly go to the other extreme. They include demographic info into the model. And that means that your model is basically ends up saying, I have got two students, they're identical except for their group status. I'm going to treat them differently. And that is something that really concerns me a lot because I get very uncomfortable with the idea of you've got two students who are identical in all other fashions, but we're going to treat them differently. I much prefer models that work for everybody, are fair for everybody, but are validated to be valid for everybody. Anyway, figuring out how we can tell if a model is equitable is an open research area. There's actually a lot of debate on this, not just in learning analytics, but also in analytics more broadly. A lot of people disagree about what makes a model equitable, but it's a really important thing to be paying attention to. I'm going to keep hitting this, aren't I? My apologies. I'm not very good with spatial reasoning. Individualization. So we want to individualize for students and try to give different experiences that help everybody succeed better. That requires first determining something about the student. Second, knowing what matters. There's a lot of things we can determine that no one cares about. Example of that, for example, in K-12 would be that, I shouldn't say no one cares about, but it turns out that in classrooms, when students are working in group work, a lot of teachers in K-12 worry about off-task behavior. Off-task behavior is actually associated with better learning outcomes if it's group work. Teachers are shutting off a behavior that's associated with positive collaboration. I'm not saying students should be off-task 94% of the time, but if they're off-task occasionally, like maybe a minute every hour or 3 minutes, that's actually good. So you gotta know what matters, you gotta determine something, and you gotta do the right thing. Here are a few things we can infer. We can infer complex learning. Is the student learning to solve complex problems that require inquiry skills? That's really important, especially when we think about an undergraduate education where we want our learners to develop very sophisticated skills. And projects like these have been able to detect the difference between successful, effective inquiry and unsuccessful, ineffective inquiry. This first one, Sale Pedro et al., involved Janice Gobert here at Rutgers. Is the student developing rich conceptual understanding in domains such as physics? These two projects actually created game situations. I showed a picture of one of them. And we can actually detect if a student understands, for example, Newton's laws for an elementary example, or machines of force and motion. We can infer robust learning and preparation. So will the student remember what they learned? A lot of learning practices involve very good success in the short term. One of them would be cramming. Cramming actually works if your only goal is to pass the test. If your goal is to remember any further, it's really problematic. Is the student prepared for future learning? So we can detect not just is the student learning now, but is their pattern of learning associated with doing better on future content? Is the student on track to stay in the STEM or career pipeline? So that's related to that kind of success prediction. Can we detect from students details? There are many students who are doing well, but are becoming disengaged with the subject and are going to stop taking it in the future, and we can detect that. Metacognition, how confident is the student? Student confidence, we want students to have realistic confidence, but if they are good at things, we want them to be confident about that, because lack of confidence, lack of identity formation is something that's associated with people, again, leaving the STEM pipeline if they're in STEM. Is the student asking for help when they need it? It's good to ask for help sometimes, right? We don't want the student who's showing up to office hours every single time because they want attention, but if a student isn't asking for help when they're struggling, that's a real problem. Is the student, conversely, persisting in the face of challenge? It's possible to detect which students are persisting and which ones aren't. Kind of these three categories of wheel spinning and kind of persisting unproductively, persisting productively, and not persisting. We kind of want to get students in that second of those categories. And we can detect who's on track for that. Disengaged behaviors in online learning. So some online learning systems give students multiple attempts at a problem, and some students will use those multiple attempts to go 1, it's wrong, 2, it's wrong, 3, it's wrong, 4, it's wrong, 5, it's wrong. I have data on one student doing that from 1 to 38, which is the right answer. That happens in a lot of online learning systems. Correspondingly, some students will do things like in an online course where you can create free accounts, they'll have the paid account and the free account. The free account will go through, find out all the answers, and then they'll go to the paid account and they'll type in all the answers. Jose Rupier, it's not on the slide, but Jose Rupier's Valiente found that actually up to more than half of accounts in most online open courses are accounts being used for answer harvesting. Carelessness. Carelessness is when you make errors despite knowing how to do the right thing. It happens when it's very time-consuming to solve stuff. Turns out that carelessness is a harbinger of worse long-term performance. Inexplicable behavior. There are some colorful terms for this one, but basically students, for example, are plotting points on a function graph in a developmental algebra course. Instead of plotting the function, they plot a smiley face. Affect, emotion and context. Boredom, frustration, confusion. You probably know what all those are. Engage concentration. That's the emotion associated with Csikszentmihalyi's flow, where you become so deeply engrossed in your activity that time drops away, the whole world drops away, and you become completely focused on just what you're doing. I'm sure that's the experience that you're all having right now. Good, I got a few laughs. Not too much off-task behavior. Curiosity, excitement, situational interest, joy and delight. Delight, by the way, is a fun one, an interesting one, scientifically interesting one, because a lot of online games, educational games, serious games, are targeted towards creating delight. But actually, delight is disruptive to the sense of engaged concentration, and there's not great evidence that delight actually promotes learning. It's a funny thing where some of the most delightful games are some of the most boring games. But bottom line is that it looks like chocolate-covered broccoli is not particularly good for people. Chocolate-covered broccoli being like, sorry. You take the broccoli, the learning, you think people don't want it, and then you pour the chocolate on to make it tasty. So these things can be detected without physical sensors. A lot of people talk about instrumenting up classrooms, and I'm not against that work. It's more feasible at higher ed than it is at K-12, but it's still expensive. It's hard work. Building good models out of it is difficult. And it's not necessary a lot of the time. You can infer everything I talked about here solely from students' interactions with properly designed learning systems. And this can predict long-term outcomes. I'm going to give a couple quick examples. One example is from middle school, and I know this is a university. Why am I giving a middle school example? It's largely because the stuff on fine-grained student interaction, for whatever reason, has kind of gone further faster at the middle school, high school, K-12. So for example, affect and engagement in middle school, kind of some of the constructs we talked about predict, first of all, standardized exam score at the end of the year. One nice thing about K-12 as opposed to many university settings is there are widely used, agreed upon measures of learning. Not saying it doesn't exist in universities, but it's much less national, much less broad scale. So in large studies, affect and engagement in middle school predict standardized exam score that year. They also predict college attendance several years later. So if students are gaming the system in middle school math, they're less likely to go to college. They're less likely to go to selective college like Rutgers. And they're less likely to major in math and science. Gaming the system middle school math, less likely to go into math and science in college. Does anyone want to guess what major what two majors they're more likely to enroll in? Quiet room.
Psychology.
Business. Business is correct. That's number 2. Psychology was a good guess. It is not actually one of them. But they're not particularly likely to go into psychology either. Social work turns out to be the other one. So I think that's actually a very positive thing. Like social work, being successful at social work involves being able to make systems work. That skill of being able to game the system appears to have some transferability. Being able to game the system might be good in business as well. First job post-college. Affect and engagement middle school mathematics predict whether after college you go to graduate school or take a job in STEM. So there's kind of this long-term validity to these kind of constructs. Another example, student interaction within a graduate school level MOOC on data science can predict whether the student will eventually submit a scientific paper in the field. So how and whether you engage is actually predictive. Now, what's really interesting is that forum lurkers, people who read everything but never post, are just as likely to submit a scientific paper as forum posters. That's particularly an interesting result because in this course, forum posters are more likely to complete the course. And there's a lot of evidence at the college level that if you post discussion forums, you're more likely to pass the class. But what this might suggest is that people who read, maybe they're not going to do as well in the current class, but they might actually do as well in the longer term. In this case, it probably also had a lot to do with the fact that, honestly, getting a certificate signed by Ryan Baker is not even really worth the paper it's printed on. I mean, honestly, like, there's no real value to that credential, but the learning is what's really valuable. Well, I like to think. So when you have this kind of data, there's a huge space of potential interventions, huge space of things you can do. So for one thing, you can create reports for the instructors. You can create reports for academic advisors. Places like Southern New Hampshire and Liberty are doing amazing things with their analytics reports for academic advisors. They give academic advisors these reports. This student, got their homework in late to this class, and this is their increased risk. I'm going to talk about this in a minute. It turns out, for example, that at Southern New Hampshire, if you don't open the e-textbook before class starts, you're at a significantly higher risk of failing the course. That's an easy thing to present that analytics. Say, hey, you haven't opened your textbook yet. Could you start to get ready? You need to. And that's especially important for the non-traditional students they serve, but I think it also has a very important role in more traditional higher ed settings. There's reports for instructors on what students are having trouble with. This skillometer comes from Carnegie Learning System, which is used for developmental math at a lot of campuses. It tells a student what they're doing well and what they're doing bad at. Also turns out to be very motivational for a lot of students. Yes, ma'am.
So, do they show the student predictors?
Some systems do and some don't. I tend to think that telling a student why they're at risk is actually beneficial because it can tell them what they can do. For example, there was a great effort at UNLV, led by Matt Bernanke, that actually kind of did a really nice job of breaking down into the model and saying, here are the specific 3 things you could do that would increase your chance of success in the course. So I think that's really valuable, personally. Especially for adults, which, undergraduates are adults. They should be expected to be able to learn from these things. Automated interventions delivered by animated agents. This is less for like you're going to fail the class, mostly, and more for like you're not doing as well in this learning environment. Stealth interventions that change learner experiences in subtle ways. I am not able to show you a picture of this, right? But different systems, for example, optimize difficulty. Optimizing the difficulty so it gets harder if someone's doing well and easier if someone's doing poorly is a really powerful technique. Who here has used like a flashcard or a language learning app? Which one? Duolingo?
Yes.
Yeah. Duolingo is a really interesting one because Duolingo is really fun. Like Van An and his colleagues have done an amazing job of making Duolingo a fun experience. It actually, no negativity meant, because I've used Duolingo myself. It's missing a lot of the stuff that people need to learn when they're learning languages. What it's good for, it's really good for. And it's amazing what a good job they do on fun and long-term memory. They're really good at some things. I actually mostly use Anki myself instead of Duolingo, but that's a subject for another day. So I want to give a few examples of use at scale. I've already mentioned a few of these. Cognitive tutor, used for developmental math as well as high school and middle school math. Automated detectors of student knowledge are used to drive mastery learning. There's sophisticated models that figure out what you know and don't know, and then you don't go on until you've learned it. ALEX, college and high school math and chemistry. Models of prerequisite structure and knowledge are used to select material for students. Big idea here being that they can quickly figure out where a student is in the curricular sequence based on their performance, put them at the right place. Some of these systems, I don't think ALEX does this, but some of the prerequisite model systems actually will say, you're getting a lot of stuff wrong right now. Let's figure out if you're missing a prerequisite from the previous class that you just didn't quite get. I think that's a really powerful technology. Project Listen. Data mining is used to determine which strategies in reading work for which students and help select which stories to give students to read. Students read a story and they actually speak it out loud, and it uses voice recognition to figure out if they're reading correctly. This is used for both elementary school reading in the United States, though not at scale, and adult reading in some developing countries where it's used with funding from the Gates Foundation to help people learn to read English. Newton. Newton enabled systems that decided what problem to give a student next in a lot of domains. Newton kind of had an implosion a couple years ago and has reinvented itself as mostly just a provider of specific curricula, but there was a period where lots of online vendors used them. Inkits. Inkits is a middle school science system. I want to give it props because it's developed right here at Rutgers. It has automated detectors of student inquiry skill embedded in an automated agent that helps students learn how to do scientific inquiry more effectively. And it's been shown by work by Sale Pedro and others to lead to inquiry skills that transfers across scientific domains. So students learn skills in their physical science class. They're able to use them in their biology class. Here's a picture. So this is Rex, and one of these animated agents I talked about. And Rex says, I think the data you're collecting won't help you test your hypothesis because you aren't designing a controlled experiment. And they can ask for more details. Or Rex says, hey, are you just playing with the buttons? Take your learning seriously or I will eat you. Fortunately, no students have been harmed in the use of Rex. Another example of use at scale, Bright Bites. Data on learning system usage and whether usage is associated with positive outcomes is provided to teachers and school leaders. So especially in K-12, there are often kind of system level decisions. We're going to use this curriculum or that curriculum. And then some teachers actually use it and some teachers don't, right? And they can say, it gives natural experiments to say, the teachers who use it, are their classes actually doing better than the teachers who don't use it? Kind of lots of natural mini quasi-experiments. I just actually gave a keynote on that last Thursday at a school leader convention in Texas. It's really neat stuff. Civitas, EAB, Course Signals, Zogatech at-risk prediction models. Another thing that's scaled, but the quality really varies, is analytics data on course participation and course success used in iterative refinement of content. This is used often in online courses or MOOCs. Brief example, University of Pennsylvania uses course design reports that my center's developed that, for example, can report for active students, where did they stop the course? You know, for massive online open courses, students often quit in the middle, and that's a perfectly legitimate thing if they only wanted to get one subject. But it's not a good thing if they wanted to complete and they just couldn't. So this graph actually shows what lecture students quit at. The first lecture is the biggest lecture, and that's a good place for people to quit, right? That's people saying, oh shoot, I don't actually want to take this course. The end of the first week is also a relatively reasonable place for people to quit, because that's people getting through the first set of content and saying, you know what, I don't really want this now that I really get to know it. But this lecture is not a weekend lecture. This lecture turns out to be a lecture where the course material gets harder. There's a specific new method that gets introduced in this lecture, and people go, ah, and they quit. This is a place where we might be able to redesign the class to be able to say, let's try to teach that specific subject better. Another example, looking at various items and saying, what's the error rate on them? The students try them the first time. The first quiz in this online course, item 5, students got wrong 80% of the time, and item 6, students got wrong 70% of the time. That's not a good thing, right? That means those items are really, really hard, and we need to be kind of figuring out why they're so hard. In general, we want students to get things wrong sometimes, be confused, struggle, think about it, but when almost everyone's getting it wrong, we're not teaching it right in the first place. So those are just a simple couple of examples of how we can use this kind of technology to make courses better. There's a huge space of potential interventions. Still a very open area for the field. We've gotten much further in what we can model than what to do with it. And that makes sense because good design, A, is hard, and B, you can't really do good design based on analytics until you have analytics. Trying to determine what works best in what context is a challenge. Just giving someone reports doesn't mean that they know how to use them. And just intervening doesn't mean the intervention works. We really need this feedback cycle of trying things, talking to people, seeing what happens, and making it better. And that's kind of just getting going in a lot of places. So there's a lot of potential. And if you remember, this talk was entitled Potentials and Limitations, right? So you might say, where are all the limitations? Why aren't you telling us about those? Well, there's a lot of potential, but there's also a lot of snake oil out there. There's a lot of school down the street from where I live, not the school my kids go to. Won't name the name of the school, uses this online curriculum where the web page says they have no published studies on it. They have no published, efficacy results. But the web page says that it makes kids learn math better because it makes their neurons grow faster than the other systems. Now, I'm not sure how using one online learning system compared to the other has the power of making your neurons grow faster. But it sure sounds good, right? Now, hopefully everyone in this room is a little more sophisticated a customer than the person who picked the system that makes your neurons grow faster, and that's why it's good. But some considerations for getting it right. So I had this question, I kind of found out. You guys have EAB. External it can be a really good choice. I've also heard that there may be some decentralization here, and people may have different initiatives going on in their specific schools or departments. If you do want to do it in-house, if you hire talent for analytics and data mining, try to find at least one team member who has expertise in the type of data you're working with. Not all data is the same, and what you do with your models in different domains isn't always the same. You wouldn't hire an education researcher to conduct a medical trial or to manage your stock portfolio. Definitely don't hire me for that. And similarly, don't hire people with experience in financial data or bioinformatics to be your entire learning analytics team. Hire a couple of those people, but make sure you have somebody on your team who has some experience with learning data. The problem is that there's not enough people with expertise in educational data to go around. Despite now having one MOOC that's continually running, a couple others that run sporadically, and one MicroMasters, and one master's degree in learning analytics, that still doesn't produce enough demand. Last time I looked, there were 600 jobs in Metro New York on Monster.com for learning analytics. All those together don't put out that many graduates. So hybrid teams seem to work. Embedding mentor consultants with expertise seem to work, but no domain expertise teams don't function as effectively. Khan Academy, I think this is one I will say on camera. Khan Academy hired a bunch of people from bioinformatics to be their learning analytics team, and they created this blog where they talked about all the great things they were discovering, and they spent the first 6-9 months repeatedly rediscovering the wheel but doing it badly. It was actually it became an embarrassment, and they took down the blog because they were like, if anyone here has heard of item response theory, one hand. It's a standard method in psychometrics that's been around for 70 years. And one of the people on their team wrote a blog post about how they discovered this idea that basically turned out to be item response theory, but they used the wrong statistical model. They did something that people in the 50s knew was wrong. That's what happens when you don't have anybody on your team who knows what they're doing. If you go with an outside team, make sure you know what they're doing and why. Trust me is just not good enough for something this important. So make sure you collect evidence to be sure that the approach you're using is working. You can try experiments or quasi-experiments. You can collect data on metrics like program completion, course evaluations, year-by-year attention, grades if it's relevant, student self-efficacy surveys, indicators of participation on online activities. I'm sure that a place like Rutgers is looking at these kind of things and saying this is really helping us. But one thing that's important is look at multiple indicators. Also make sure you're getting a solution customized to your needs. I think probably EAB is sophisticated enough to do this, but I'll still say some of the things to think about. Take the problem of college retention analytics. Some vendors, again, I don't know about EAB one way or the other, so I'm not trying to criticize them individually. Some vendors build one model once and then they reuse it for every client, sometimes with radically different clients. And there's a story out there about one of the larger vendors actually doing that and using models, taking them from a university that is similar to, say, Carnegie Mellon or Case Western Reserve, and then using it on universities that would be similar to Rutgers Newark. And that's really dangerous. Or they might build a model with no data at all. One British vendor was found out to have just made up their model out of whole cloth. Ideally, a university should be using a model built and validated on data from their own university. So Rutgers should be using models built on Rutgers data. If that isn't possible because of data limitations, the models should minimum be developed and tested on data from multiple universities similar to theirs. But you want to make sure that your models test on the right data, because if not, it's probably not going to be very good. An example of this in a paper that I recently submitted that's not at the university level is a K-12 thing. A lot of school districts use what's called the Chicago model. It was developed about 20 years ago on data from, guess where? The city of Chicago. Turns out the Chicago model does really poorly in West Virginia. Not shocking, right? But why is that noteworthy? Because a lot of people nationwide have used the Chicago model, regardless of where they're at. I think the same thing occurs at higher ed, and we just don't see the data. In part because one big problem is that for learning analytics at higher ed, aside from one paper by Civitas and a paper by Marist College and a paper that University of Texas Arlington is working on, I know of no papers that go into full detail on the models for this kind of undergraduate retention analytics. There's a lot of papers talking about these systems, but those are the only ones that really go into full detail and quality. There's a couple on course signals from Purdue that talk about how the model did outcomes, but don't talk about what's in the model. Understanding what the model means. Ideally, you won't just get a prediction or a huge number of indicators. Imagine getting 400 indicators back, but you'll get information on why a specific prediction is made, why a specific learner is at risk, why specific curriculum material is less effective, or why a collaborative team is less effective. In interpreting this evidence, it's also important for the people getting the information to get some training on what the indicators mean and the context they occur in. Many indicators are context specific. Like a lot of what you'll see on analytics reports treats indicators like they're universal. Here's just one example. when a student opens an e-textbook. So not having opened an e-textbook on the first day of the course catches most of the students will fail, but it also catches many students who won't fail, right? It's a good indicator, but it's got, to use technical terms, great recall. It gets everybody who's at risk, but low precision. It gets a lot of people who aren't at risk. It can be used, but you have to use it in a very sensitive intervention that suggests something without really being too negative towards people. Not having opened the e-textbook on day 14 of the course is almost always associated with failure. But it catches a lot of students who don't, it doesn't catch a lot of students who do fail, right? So whereas this one might want a general suggestion, this one you might want a giant red flag, like you should either drop the course or change what you're doing immediately because you're in deep trouble. Another big piece of advice I have is to look further. Most of the use of analytics in higher education is focused on immediate retention. Will the student pass this course? Will the student drop out this semester or next semester? That's perfectly good, it's important, but it misses a lot of longer term indicators. A lot of people are at risk in ways that doesn't play out for a few semesters. You know, fine-grained behavior now can predict big outcomes later. As discussed earlier, engagement in middle school math associated with college attendance. Participation in a MOOC course leads to participation in the field, differences in these. So ideally, and Rutgers should, everybody, I shouldn't just say Rutgers, everybody should be kind of setting themselves up to be able to do this now if their data systems aren't in place to do it. You know, so predict as far as you can. Who is on track not just to stay until the next semester, but to graduate from the university, succeed in their career. This involves stuff at the development and alumni offices. And they vary greatly in the quality of what they're collecting and the usefulness. Succeed in their career, that said, actually, it's easier than it used to be. When I wanted to do a longitudinal analysis from middle school to first job post-college, my lab was able to go on LinkedIn and find out a lot of our data. So who's going to succeed in their career? Who's going to be a credit to the university? As far as I know, almost no one's looking at this one in a systematic fashion. But really, we should be thinking about, I think, for example, some instructors have this inspiring effect on students that transforms their lives. I mean, if anyone here remembers Randy Pausch's last lecture like a decade ago, he talked about Andy Van Dam, this faculty mentor who had this incredible influence on his career. And in fact, Andy Van Dam was my instructor freshman year. Andy was an incredible help to my career. My career probably succeeded in a large part because of Andy's help. Dana Boyd at NYU, Andy had this inspiring influence on her as well. So there's these instructors. If we can identify these instructors, figure out what they're doing by kind of looking at, Andy's a well-known public example because of Randy's last lecture, but there's a lot of instructors like that. Correspondingly, there's a lot of instructors who actually have this really negative impact on students. I had an instructor when I was an undergraduate who caused me to change my major. He had the gatekeeper course. I was injured. I was injured in an accident. He was so inflexible about my injury that I had to drop his course, didn't want to retake it, so I changed my major. Learning analytics is probably happy. Linguistics, who knows? Maybe it was very much for the good. Maybe I would have been a very second-rate academic in linguistics. So, big idea. Thanks to the big data becoming now available on student learning and modern learning analytics methods, we can make inferences about students in real time that are predictive of students' long-term outcomes. The eventual goal is to track a student's engagement now, predict the longer-term impact, intervene to help re-engage students and support their learning. In other words, our goal isn't to predict the future so much as it is to change the future. And that can help, I think, to create a modern university more sensitive to individual learners' needs. There's lots of challenges here. There's lots of things that make it hard to get right, and lots of pitfalls where we can make a model that looks good, but actually it's systematically biased against certain students. Or we can make a model that's very good at promoting short-term retention, but doesn't actually capture the longer-term goals. Even things like, is this student going to drop the course? One very insightful thing that the Purdue Course Signals team talked about in their papers was there are some students who it might be good for them to drop a course and take a different one, right? And part of what their models did was tell students, you have a very high chance of failing or dropping this course, so that the student could decide whether, if you do that early, the student could decide if they want to change or if they want to take a different course. You know, for example, maybe my destiny really wasn't in linguistics, and it's a good thing that that specific instructor basically forced me out of the course. So there's a lot of challenges, there's a lot of opportunities as well to make better outcomes for students. Brief commercial before we open for general questions. If you want to follow our research papers, we have a Twitter and Facebook feed. It's low traffic. You're only going to see about 2 or 3 posts a month because it's not for, I don't post on like what I had for lunch. I post on major scientific results coming out of our lab. If you want to find our papers, they're all available online. Google me, Ryan Baker. And also we have a MOOC on edX, Big Data and Education. You can get the MOOC and activities anytime on edX, or you can go just to my webpage and find the YouTube links for the videos. So thank you all for your attention, and I'd be glad to comment more, answer questions.